I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class and just ask you to help us to use the time wisely, that we would, again, glorify you what we do and understand a little more about linear algebra together, Lord. In your name I pray, Lord Jesus. Amen. So I gave you a list of examples last time, but we just throw a couple more up there because they're kind of, well, I do hope you'll read my notes, obviously, right? So sometimes always I don't get to put everything in the notes on the board. The notes are almost always more expansive than what I can write on the board. But a couple more examples of vector spaces, because I think I missed a couple notes. So like one, we could have Z mod a prime, n tuples of that. So this would be something like, x1, x2, x sub n, such that x sub I is an element of Z mod a prime for 1 to n. And this is naturally a vector space over Z mod the prime. And just in case we're not understanding each other, 0, 1, 2, all the way up to p minus 1, done modulo the prime p, that's a field, it's a finite field. And like the addition of addition and scalar multiplication is just the same one we know from like Rn. But this is also a vector space. Now I guess I did Fn last time, right? F to the n. So in the case F equals to Z mod p, that's still a legit vector space. Another one, I could talk about R bracket x. And this is the set of, let's write it this way. It's the sum I equals 0 to infinity of c sub I x to the I, such that finitely many c sub I are not equal to 0. And here c sub I are elements of the reals. This has a name, of course, and so if I have like f of x, g of x in R of x, all right, meaning f of x is like the sum I equals 1 to infinity of c sub I x to the power I, and g of x is sum I equals 1 to infinity of like b sub I x to the I. Then if we were to define f of x plus g of x, we could do that. And if we add a constant times f of x, we could do that. But I'm going to let you guys do it. So you guys tell me what to put as my coefficient of x to the power I here, what to put as my coefficient of x to the power I there. You can do it. Someone try, yes.
Is it not just
CI plus BI, we have a winner, yes. And very poor choice in scalar. Let's change that C to an alpha. Okay. How about alpha times what? Alpha, F had the alpha CI, right? Do you guys know the name of this set? What is this? This is polynomials, right? These are the polynomials with coefficients in R. Let me just bump this example up a notch. I mean, is it clear that, okay, let's think through it. if finitely many for f and finitely many for g are non-zero, there's still only finitely many non-zero down here. And there's still only finitely many non-zero down here. Therefore, f of x plus g of x and alpha times f of x are again polynomials, which is a quick argument to show you that this set is closed under my alleged vector addition and scalar multiplication. And you can check the rest of the axioms. But, oh gee, you know, if you want to swap out r for w of x, where this is a vector space over f, you could work with polynomials where the coefficients were vectors. This would still make sense because you could still add the coefficients and you could still scalar multiply the coefficients. So we could easily work with polynomials where the coefficients were matrices, for instance. And we'd still add them just the same. For example. Of course, you can swap this R out for a Q or a C or whatever field floats your boat, right? The other thing we could do, though, is work with polynomials with more than one variable, right? Like another cool example would be R of xy, right? Which you could write a typical thing in the form sum over I and j equals 0 to infinity of like Cij x to the power I, y to the power j, such that finitely many Cij not equal to 0, okay? So that's kind of another nice whole family of examples you could play around with, bivariate polynomials. So most of these examples I'm talking about today, except for the first one, these are infinite dimensional, whatever that means, all right? We're not going to be able to build these spaces as a finite linear combination of a given basis, as we'll learn. I am putting the cart before the metaphorical horse very badly with that comment, but you'll forgive me. All right, so last time I introduced the subspace notation. I see I skipped past an important theorem I should probably mention. My bad, guys. So this is theorem 2.1.15. And this theorem says some very obvious things that are not these are not axioms of a vector space, right? But these are consequences of the axioms. All of the things I'm about to write can be proved from the axiom through kind of, annoying step-by-step arguments. Well, they're not annoying, they're interesting. So like 0 scalar multiplied by x is equal to 0. 2, c times the 0 vector is equal to 0. 3, minus 1 scalar multiplied by the x is equal to the negative x, the negation of x. And 4, if cx is equal to 0, c times x, I'm missing a dot there, then c is equal to 0 or x is equal to 0. So this is for all x in the vector space, for all c in the field, for all x in the vector space. And then it turns out these are pretty much stemming from this lemma, which is the so-called law of cancellation. Law of cancellation, which says that if a, x, and y are vectors, and x plus a is equal to y plus a, then x is equal to y, right? So all of these things we kind of take for granted, right? Like, I personally use these when I'm working with matrices or vectors without even thinking in terms of simplifying, right? But these four properties and the law of cancellation can be systematically derived from the axioms I wrote down last time. And if you look in the notes, there's like a page where I do that step by step. Every so often on test one, I'll give you the actual definition with the axioms enumerated as they are. And then one of the questions would be like to prove one of these using step-by-step axiom logic, right? So I do sometimes ask that. All right. So last time we had the, subspace. So remember, if V over F is a vector space, then S, a subset of V, is subspace if we take addition and the addition from S cross S is into S, and scalar multiplication from S, the field cross S into S, make S a vector space over the field. Then we say that S is a subspace of V, right? Now, so I'm to be fussy, right? To be fussy, this, let me be fussy for a second here. I say plus and dot like that, right? But what do I really mean? What do I really mean? Let me be a little bit more pedantic. So plus and dot are given for the vector space in this discussion, right? Remember last time we read it out? The 10 axioms. So like the domain for plus was what? Originally, it was V cross V, right? And the domain for scalar multiplication was F cross V. So technically, this is the restriction of the vector addition to S cross S. And this is the restriction of the scalar multiplication to F cross S. All right? The original vector addition is from V cross V to V, right? And the original scalar multiplication was from F cross V to V. And this is like a critical point. For it to be a subspace, it has to be a vector space with respect to the inherited vector addition and scalar multiplication in the space. Every so often you find a subset which can be made a vector space with respect to some new definition of vector addition. All right, but that wouldn't actually be an example of a subspace. All right, let me give you a precise example of this, a subset which is not a subspace. So like example 1, we could take this plane in R3. It's not really important that it's 3 dimensions. It's just more fun to make it 3-dimensional. And I'm supposing this plane goes on and on. This is my S, right? So S is a subset of R3. And it's certainly non-empty. All right? Now here's the thing. If I use vector addition, all right? So maybe this is a point in the plane P. But if I went to this vector here, right, say A, and this vector here, say B, and if I look at A plus B, it's up here, right? That is not an element of S, is it? So I have these two vectors that are pointing to points in the plane, right? So they're in S, but yet their sum is not in S. So S is not a subspace. S is not a subspace. With respect to native vector addition in R3, which of course is based where? Based at the origin, right? Our standard definition of vector addition is presupposing that the vectors are based at the origin, essentially, right, geometrically. Nevertheless, if this is a plane, if we talk about two tangent vectors in the plane, you see, right? If I have two tangent vectors in the plane, if this is my vector and this is my vector, you know, there is a natural way of adding those tangent vectors in the plane and getting another tangent vector into the plane, right? I mean, so I don't want to go through the mechanics of that, but that is not the standard vector addition. That's something else, right? Geometrically, it's easy enough to understand. I can take tangent vectors in the plane, add them tip to tail, they're still in the plane, right? It does make you wonder what 0 is. Oh, it's a 0 vector, isn't it? Yeah. So how do you implement that in terms of formulas? Well, I'm just going to leave that sitting there to bother you. We're going to go on. We're going to go on. All right, so I told you guys last time the subspace test, right? And what did the subspace test say? It said that, I'm not going to write it out again, but it said that if the set is not empty, and if we pick two things in the set, right, then the sum of those and the scalar multiple of them is again in the set, then it's a subspace. Right, this is the subspace test. So, example 2, we could talk about, you know, A and say F, M by N. We can talk about the null space of A. What was that defined to be? X in Fn such that what? Ax equals to 0, right? Is this a subspace of Fn? Let us prove that it is using the subspace test. That's all right with you guys? So let x comma y be in the null space of A, then of course Ax equals to 0 and Ay is equal to 0. Hence A times x plus y is Ax plus Ay is equal to 0, and I mean that's 0 plus 0, which is 0, and A times say alpha x is alpha times Ax is equal to alpha times 0, which is 0. Which, so x plus y and alpha x are in the null space of A for any alpha in the field, right? Is that enough for us to conclude that the null space is a subspace of Fn? You can tell from the intonation of my question the answer is no, but why is the answer no? Oh man, I guess I give you the answer to the thing I left you hanging on page 57. There's some formalism there to make good on my tangent space thing. Yep.
We have to show it's
Non-empty. Ah, yes. Note A times blah is equal to 0. Therefore, the null space of A is not empty. Fill in the blah. I heard a 0. I'll take that. Yes, 0 times any matrix is 0. 0 is in the null space. That's always a good thing to check, especially if you're in the dark about whether or not your example is a subspace or not. What a great thing to check on. If there is a 0 in there, it has hope of being a subspace, right? But if you're in the dark about whether or not a subset is a subspace, if you go looking for 0 and it's not in there, well, you're done. It's not a subspace. So you found a contradiction to the possible, like showing there's not a 0 suffices to prove it's not a subspace, right? Showing that the vector addition is not commutative suffices to show it's not a subspace or a vector space. If you can violate any one of the axioms, right, with respect to a given subspace, then it's not a subspace, right? But anyway, this one is, hence, I already used hence, let's use a different word, therefore. The null space of A is a subspace of, in this case, Fn, right, by subspace test theorem. So as I was telling you guys, I had I had threatened to prove this theorem this time, but I'm going to chicken out on that and ask you just to read the notes. The proof is very silly. The proof of the subspace test theorem is essentially that all that you need for the addition and scalar multiplication to be honest to goodness vector additions and scalar multiplications for your subset is that they're closed. That they're closed under the operation. And that's exactly what you're checking. You're checking a closure of addition and scalar multiplication, right, for the alleged vector addition and scalar multiplication for your subset. The other things like commutativity of addition, associativity, existence of inverses, all that other stuff comes for free because it's just essentially inherited from the vector space structure. So that's super nice. Yeah.
This could be silly, but I'm still kind of confused on example 1. So, like,
Oh.
would the V be R3?
Well, so in this case, here the V is R3 in terms of what it's not a subspace. If we work with V sub P, which is equal to pairs P comma, say W, such that W is an element of R3. In other words, based vectors based at P. Then in that context, if you take like P with 0 is the 0 vector for your set, like we call it 0 sub P or whatever. And if you take if you take P comma A plus P comma B, what you get is P comma A plus B. In other words, vectors based at P, say you take P essentially serving as your origin, and you do tip-to-tail vector addition from there. That's the formula. The formulas for it are on page 57. But this is not the standard definition of vector addition. These would be vectors based at P addition. With respect to that notion of vector addition, it is true that S is a subspace. But that's not the standard notion of vector addition.
Okay, I was more confused about it.
Uh-oh.
I'm sorry, I probably didn't describe it well.
You're fine.
So it's got to be, like, if it's in the set S cross S has to map to S. It doesn't matter if it maps to the vector space.
That's right. Exactly. S cross S has to map to S again. And the fact that didn't happen here
And that's why it's not.
game over, right? If, on the other hand, we actually make good on my picture and, do like this and then that, well, then this right here, of course, is the A plus B, which is still a based vector in the set S with respect to the based vector addition. We do based vector addition in physics in Calc 3 all the time. We don't even think about it. But in linear algebra, the standard examples are vector addition is based at the origin. That's our definition. A plus B is A sub I plus B sub I. There's no point of attachment in there or anything. Well, the point of attachment is 0. But anyway. So this is a subspace. All right. So the long story short is with respect to the standard notion of vector addition, subspaces have to be like lines through the origin or planes through the origin. Like your subspace has to contain the regular origin. Otherwise, it's not a subspace with respect to the usual notion. Yeah. So then the other thing I mentioned last class, I seem to be in a review today, was spanning, right? We talked about spanning. We should talk more about spanning. What's our definition of span? Did we define span in here yet? We should. Let me start at the beginning. What is the span of the empty set? Yeah, what's going to be our definition of what's the span of the set containing nothing? The empty set? No, we don't want that. 0. Correct. That is what we need to do in order to not have exceptional cases to like dozens of theorems. Okay, so this makes 0 fit nicely. By the way, one of the things I should have told you already if I was more on my game in here at this time. And so 0, the set just containing 0, is a subspace. 0 plus 0 is 0, C times 0 is 0, right? So the set just containing 0 is a subspace. What is another automatic subspace of V? How about the whole space itself, right? Every vector space has 0 as a subspace and also itself as a subspace. These are kind of silly, always there examples. So this is an example of span. This is the definition, actually, okay? I can't derive that or anything. But on the other hand, if S is, let's say, a subset of a vector space V, then the span of S, all right, is equal to the sum, I equals 1 to k, of C sub I, S sub I, such that Ci is an element of the field and Si is an element of S for I equals to 1 to dot 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 to k for each k in the natural numbers. So let me put it into words. The span of S is the set of all finite, shush, phone is ding-donging me. So this is a set of all finite F-linear combinations taken from S. That's what I'm trying to say with that set theory there, okay? I'm not saying that S is a finite set. Do you see that? S could be infinite. Nevertheless, the span is taken to be the set of finite linear combinations. For example, where am I? Example 3. If I have my set is the set of monomials, 1x, x squared, right? X cubed, and so forth and so on forever and ever, amen, right? The span of S, right? It's the set of finite linear combinations of these monomials. That's exactly our example from earlier today. This is, as you can see, the polynomials in X. All right? Now, in the case that if the number of things in S is equal to n, which is a natural number, in other words, it's like not infinity, right? It's not something that's bigger than the natural numbers, bigger than a specific counting number. If you have a finite set, then we don't need this business up here. We can say it more simply, like we did in 221, which is what? Span of S is what? It's just, C1, S1 plus da 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 plus Cn Sn, right? Such that the C's are in the field. Let me rewrite that in the better notation. In other words, the span of the set just containing S1, S2 all the way out through Sn is simply the sum I equals 1 to n of C sub I, S sub I, such that C sub I is a number in the field. All right. That's the span. See, for a finite set, we don't have to take the k to vary, right? For an infinite set, you have to allow yourself to take finite linear combinations of size 10 or size 20 or size 200 or size 2 million. Like, right? I mean, these are all finite. But if I'm just taking a span of a finite set, then it's simpler. I just always use the full size of the set and just allow myself the possibility that these are 0. Right? You can do that. Any questions? Okay. So, how did we... I think the fundamental lemma we should prove well, maybe proof is too strong a term for me today, but the fundamental lemma we should discuss, all right, proposition. A linear combination of linear combinations is a, you guessed it, linear combination. All right. So I guess we need some notation to like prove this proposition, right? So let's suppose that we've got like V I got to pick a letter. So x1, oh goodness gracious. I'll pick some letters eventually, guys, here. So Vi is equal to a sum, Cij, j equals 1 to, I don't know, n sub I of, let's say, W sub j. Actually, I don't want to assume that all the linear combinations have the same. I guess I should put a W. I'm sorry, guys. I'll get it eventually here. Wij. All right. So for Wij in the vector space and Cij in the field. All right. So yes. I think so, just because of the generality I'm trying here.
So are we going to put that like in the sum part too, or does that not matter?
Doesn't matter. I'm not doing a sum over I here. For each I have a sum over j, but I need I as a label. See, because like V1 is being built from like the sum over j equals 1 to n1. Of C1j, W1j, whereas like V2, I'm building from j equals 1 to n2, C2j, W2j. So I'm using them to separate my lists. All right, so there's probably a better notation that could be picked, but this is the notation that I picked today. So each one of these, this is a set of linear combinations, right? Every one of these is a linear combination. So I want to take a linear combination of these linear combinations. So what's that look like? I take a sum, let's say I equals 1 to, I don't know, big N of B sub I, V sub I. All right? But what is the V sub I? And here the B sub i's are elements of the field, right? Okay. Well, B sub I, then you got the sum j equals 1 to n sub I of, what did I say, Cij, Wij, all right. But that, my friends, is the sum over I equals 1 to n, the sum over j equals 1 to n sub I of B sub I, Cij, Wij. That's a linear combination. I mean, so this, you know, if I wrote it out, I may not write it out, but this is a linear combination once more. So, I mean, it's not a terribly profound proposition, but it's like kind of important to notice that a linear combination of linear combinations is again a linear combination. All right? I claimed that if something's a span, it's a subspace, right? So theorem, S a subset of V, then the span of S is a subspace of V, right? That was my theorem. Now we can prove that theorem, right? If S is empty, then what? Then the span of S is what? It's the span of the empty set, which we defined to be 0, which, by the way, is a subspace of the vector space. So we're good in that case, right? Else, what is the span? It's a set of finite linear combinations, right? If x and y are in S, in the span of S, right? And alpha is in the field, then alpha x plus y is in the span of S. Why? Why is that? Because x and y are linear combinations by assumption, and that is a linear combination of the linear combinations x and y, so by the proposition. Well, let me just leave it at that. I think saying more doesn't really help. What remains to show then? In the case that it's not empty, we still need to show that it's... In the case that S is not empty, we still need to show that the span of S is not empty to use the subspace test, right? How can I show the span of S is not empty? S is not empty, right? Hence, there exists X in S, right? Notice that 0 times X is, which is equal to 0, is a linear combination. Hence, 0 is an element of the span of S. And so span S is non-empty. Therefore, by the subspace test theorem, we have the span of a set is a subspace. This is kind of typical of arguments that involve the empty set or not the empty set. If it's not the empty set, it means there has to be at least one thing. And then you do something with that one thing, plus the axioms that are involved to prove what you want. In this case, I just need to rely on the thing I didn't prove today, but I pulled out of the thin air, that 0 times x. Where was that an axiom? 0 times x has to be 0? Was that one of our axioms? I think it was. It's definitely a consequence of our axioms, though. 0 times any vector is the 0 vector. Yeah. So like as a general point of order, if there's anything I miss in the lectures as we're going, I'll try to like save those things, whatever they are, to like circle back to on our question day right before the test. If you guys still want like further comment on it, if you like my notes aren't clear and whatever, yeah.
You have taught everything you need to issue comments so far, correct?
I think so.
Okay.
Yeah.
Okay, just making sure.
I mean, there may well be something that you guys need to add to it, some kind of secret sauce, Let's see here. I'll take a quick look since you asked. Oh, we have linear independence. Let's talk about that. Yeah, we need to talk about linear. You guys know about linear independence from the previous course, but we should talk about linear independence. I think that's probably the missing link, because I was supposed to talk about missing linear independence today, right? We can still do it. We'll get started at least. So span is a subspace, is huge, right? So, and by the way, if you have a set and the span of that set is the whole subspace, then that's said to be a spanning set, right? Or a generating set. If you have such a set, a generating set, it becomes interesting to ask, is that generating set minimal? You know, could I take something away from the spanning set and still get the whole thing, you know? And that's where linear independence comes into play. So here's the definition. If S is a subset of V, then S is linearly independent which we will gleefully abbreviate as Li, if for any, let's say, S1 through S sub k in S and constant C1 through Ck in the field, we have C1 S1 plus plus Ck Sk equals to 0 implies C1 equals to 0, Ck equals to 0, right? In other words, if you set a linear combination, if you set any finite linear combination of elements of the set equal to 0, it must be that that is in fact the trivial combination. The coefficients must be 0 if that happens. This is how we define linear independence. Now linear dependence, right? Linear dependence means S not linearly independent. Okay, so there you go. So, silly example. Well, not too silly, I suppose. Example, where am I? 4, 5? 4? I don't know. What's that?
It's 3:57.
When does this class end?
4 or 5.
Oh.
I thought you were asking me like what time.
Oh. Thank you. That's very helpful, actually. So if I take the set just containing 0, it doesn't matter what vector space I'm in. This is a linearly dependent set. Why? It has 1 times 0 equals to 0, right? And that does not imply 1 is equal to 0. You see, this is like C1 S1 equals to 0, and it does not imply that C1 equals to 0 like it needs to. So the set containing, and it doesn't matter if it contains just the 0. If 0 is part of it, game over, right? Any set containing the 0 vector is linearly dependent. If I put 0 and then a bunch of stuff, whatever, as many as you like, then if you look at, 1 times 0 plus, C2 times x1, Cn times xn equals to 0, that does not imply well, I'm still not saying it the right way. I mean, if you, well, I guess I got to put C1 here at the start, right? That's just a dot in the, oh, there we go. So if I have C1 times the 0 vector plus all this, right? I cannot rule out like C1 being non-zero as part of the solution, right? Sorry, I don't like the way I'm saying this at the moment. Let me go on. Do you guys remember any other ways to look at linear independence? So this is like my preferred definition is set a linear combination equals to 0. That has to imply all the coefficients are 0. There's like a couple of other equivalent ways to state it, right?
I'm not sure if I'm gonna say this
That's fine.
quite
Go for it.
accurately, but the way I see it is if there's an entry in, if there's like there's one entry in each pivot column that is, should I just give you an example?
That's fine. So you're thinking of like, specifically if we have like a set of vectors, of column vectors, like what is it?
So yeah.
Yeah.
I'm thinking like, if it's like one,
Let me say like you have V1,
can you write a matrix down?
so VK in, yeah, I will, in Rn. And if you look at the reducer echelon form of those,
Yeah.
right?
If it's independent,
It should be what? That these are all what?
like one at the top
Uh-huh.
row, and then 0, 0, 0.
Right.
And then 0, 1, 0, 0, 0, 0.
And exactly, and so forth and so on until you get. So in other words, in our notation, E1, E2, EK, since I made up something with K, right? That would be an explicit test if we had K n-dimensional vectors. Like if we row reduce them, that happens. You're exactly right. They'd be linearly what? Dependent or independent? Independent, right?
So this definition, are we assuming anything about S, or is it just any set?
Any set. Doesn't have to be finite, but it's tested by finite linear combinations. So for example, we can check the linear independence of the monomial generating set for polynomials over there.
Okay.
Like if we think about the set 1x, x squared, and so forth, let me call it S, right? This is linearly independent, right? Because if I take a sum, I equals 0 to infinity of, ci x to the power I with finitely many non-zero, right? In other words, a polynomial. And if I say that polynomial is equal to 0, you guys know the drill. That is true if and only if what? The c sub i's must what? They must all be 0. Polynomial is only 0 if its coefficients are all 0. That testifies to the fact that the monomial basis is, I used to use the word basis, whatever that means, but the set of monomials is linearly independent,
Okay.
right?
Okay. And then I think there was another question. What was it?
So, but to test linear independence, you're right, for column vectors, we can do row reduction stuff, and like if any one of the columns is not a pivot column, then it's linearly dependent. And the column correspondence property we talked about will actually show you how to build that column from the other previous pivots, right? That's true, absolutely.
Oh, yes.
Mhm.
So this definition is helpful because it's more general than just vectors, right?
That's right.
And, yeah. So are we going to see anything other than vectors realistically on exams?
Oh, yes, absolutely. Matrices, functions, just things about abstract vector spaces, for example.
Okay.
Yes. Yep.
If the null space is 0, is that linear independence? Like, is that the same thing as saying about all the pivot columns?
So is the null space of A linearly independent? No, it's got 0 in it. Any set which contains 0 is not a linearly independent set. Right? So
Like when, well, I guess in 221 when we did like rank and nullity, if the null was 0, wasn't that implying linear independence?
if the null space is 0, that means that the nullity is 0, which means that the number of non-pivot columns is 0, which also means that every column of the matrix is a pivot column, which we could also say that the pivot column, we could also say that every column in the matrix is linearly independent. So the null space being 0 gives us linear independence of the columns. But when I talk about linear independence, I'm talking about a set. And when we talk about the null space as a set, it's a linearly dependent set because it's got 0 in it. Game over. 0's in there. You gotta look. Any subspace is linearly dependent because it's got 0 in it. The vector space as a whole is linearly dependent because it's got 0 in it. Oh, you're cool. It's okay. So what I was fishing for, you guys, is there's like a couple of other equivalent characterizations of linear independence here. One is that we can take one of the vectors and write it as a linear combination of the remaining vectors. That sort of is nakedly what we mean by linear dependence, right? You can write one vector as a linear combination of the others. That's linear dependence. But another popular one is if we have linear combinations of the set, two linear combinations equal, right? Then the coefficients of said linear combinations must match up. We can equate coefficients for a linearly independent set. So those are the kind of like my three go-tos, the definition and the two I just said. Those are how I characterize linear independence. So the next order of business, of course, is to talk about basis. What's a basis in a vector space? Any ideas? Let's see here. So like next class, what your mission ones do? I think I've said everything that there is to say about mission one. You know, so I think you should be able to do it most likely. But next time, actually, I'll try to finish up the story about what I was just saying about linear independence, because that's important. But a basis, right, is a what? So a basis beta for V has two things. One, beta is linearly independent. And number two, the span of beta is the whole vector space. This is what we mean by basis. A basis is a linearly independent spanning set. I've used the word dimension a few times in here. The definition of dimension is the number of things in beta. That's the dimension of V. In the case that we were talking about a finite generating set, the dimension is just the number of things in the basis. And we can prove, in fact, that that number is independent of our choice of basis. So like dimension's an invariant of the vector space. But in the case that the basis is infinite, right? Like this one, what would we mean by number here? You guys remember from Math 200? What do we say the size of a set that can be enumerated by a counting number is? It's what? Cardinality, right. So the dimension actually is the cardinality of the vector space. It's the cardinality of the basis. That's how we're going to define dimension in the infinite context. And we'll see even in that case, the dimension is an invariant. You can't have a vector space that has one basis with cardinality aleph naught and another basis with cardinality of the continuum. If you've got a countable basis, any other basis must be countable, right? For example. And like this part of my book, listen to me, my notes, I stole from my brother. All right, I will admit it. It's completely thieved from my brother, who's an honest to goodness algebraist. It gets deep. It gets really deep in that next section. So we're going to look at it. I'm going to project it. I'm going to talk through it with you. But if you don't all understand it, like it's not the end of the world. But it's good for you to see these arguments because they are touching on some deeper things that we don't really hit in the math major except for here. So it's good for you to be exposed to these kinds of things. But at the same time, I have no earthly idea how to test on them, except to just ask you to regurgitate what I tell you. So don't feel too